This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Yep. Okay. Okay. That's all right. We'll do whatever is next. Just need to log in. So what we will need to go between the camera and, okay, I'll just find this first. This was what, tutorial 3, right? The workshop 3. I'm just thinking maybe the best way to do it is then to just use the computer so I don't swap between document camera and, let's see. All right, so, okay, so we will look at this set of tutorial problems. The first question is given here. So certain servo system has dynamics dominated by a pair of complex poles and no finite zeros. The time domain specifications are given here. So rise time smaller than 0.6 seconds, overshoot, percentage overshoot less than 17%, settling time less than 9.2 seconds, and you are asked to sketch the region in the complex S-plane for which the poles should be placed such that all specifications are met, all right? And then the second question is indicate the specific locations that will have the smallest rise time and overshoot of smaller than 17%, and also meet the settling time specification exactly at 9.2 seconds. So since this actually requires a bit of plotting, you know, I'll just go swap between solutions. So here are the solutions, and here are the questions. So we will be swapping between solutions and questions, and we will work through it step by step. So what is described here? It says certain servo system has dynamics dominated by a pair of complex poles, no finite zeros. So what this tells you is that the transfer function can be written in this form, right? So this transfer function has no zeros and two complex conjugate poles, right? So what is this? Just first turn off this, all right? This was done in the lectures. So the poles of this transfer function can be written in terms of the real parts and imaginary parts. So if you just solve this equation, so denominator, you set denominator equal to 0, solve for the solutions, you will get the poles. So the poles can be represented in this form, and this was done in the lectures, right? It's useful to repeat this because then the formulas that we will present for rise time, settling time, they do use omega n, zeta, and omega d. Sigma. So it's useful to just remind ourselves what they are. So the poles of this transfer function can be written as minus sigma, where sigma is equal to this zeta times omega n. And then you have plus minus j is the minus 1 square root of that. And then you have this omega n square root of 1 minus zeta squared. I remind you that the imaginary part is sometimes called omega d, or damped frequency. Sigma is the real part. And then omega n is the natural undamped frequency, and zeta is the damping ratio. So if you represent the poles of this transfer function in complex plane, you can represent them either using the Euclidean coordinates. Then you have minus zeta omega n and j omega d. They are the coordinates, Euclidean coordinates of the poles. Or you can represent them in these omega n zeta coordinates. So omega n is the distance of the poles from the origin. And then this theta angle, that the line connecting the pole to the origin and the imaginary axis, this angle is really arc sine of the damping ratio. So when damping ratio is small, this angle is small. So you are close to the imaginary axis. So in lecture notes, we presented several formulas for relationship between settling time, rise time, and overshoot, and various features of the poles, or sort of properties of the pole. So in particular, we related settling time to the real part of the poles, right? So we said that settling time should be 4.6 over this sigma, or sigma should be 4.6 over Ts, right? So we are asked to make settling time smaller than 9.2. Now, this formula is given in the lectures, right? And this was done for 1% sort of margin around y infinity, right? So the derivation of this formula can be found in Olgata, but we will just use it. So you are given Ts that has bound on Ts, and we know the relationship between Ts and the real part of these poles, which is sigma. So this relationship holds for this class of transfer functions, and we are given a bound on settling time. So we know now from this formula that zeta times omega n, or sigma, right, sigma, should be greater than 0.5, because we just sort of take 9.2 down, take zeta omega n on the other side, and you just get 0.5. So what does this mean for our poles, where our poles should be in this shaded region? So you look at minus 0.5 vertical line intersecting real axis at minus 0.5, and then in this shaded region, if the poles are in this shaded region, then we would satisfy the requirement on the settling time. Now, in this case, since the transfer function is second order, right, then these formulas are exact, right? But if the transfer function was different from this transfer function here, then if we still have dominant poles, so two poles are very close to imaginary axis and they are dominant poles, and all other poles are far away from the imaginary axis, then if this same inequality holds for dominant poles, then that's a good rule of thumb. We would still use these formulas, but they wouldn't give us exact things. They would be used as a rule of thumb. So the first question, the first actually specification on, well, the third one actually, we started with the third one. Settling time specification was given here, and we translated this into locations of poles of this transfer function. So the poles need to be in this shaded region to satisfy that settling time constraint. So that was just one of the constraints. We obviously need to satisfy these other two. So we were asked also to look at the overshoot and rise time. So let's look at that. So if the overshoot is less than or equal to 17%, then okay, so now this is something that I wasn't prepared for. So in the book and in the lecture notes, I gave you a relationship between zeta and MP, overshoot. So if you go to that diagram, you will just see that for 17% overshoot, there corresponds zeta 0.5. So that's taken from a diagram that I gave you in the lecture notes. So since zeta should be greater than 0.5, then the angle of these lines, that determine the region where our poles should be, is obtained as arc sine of zeta, which is 0.5. You find that the angles should be 30 degrees. So again, if you are in this shaded, by the way, this shaded region is not, these horizontal lines are there just because we consider things on bounded set, but actually the region is really bounded by these two lines that are sloping at 30 and minus 30 degrees, right? And it goes forever, right? We are not chopping off. So these sort of horizontal things are just because we consider things on a bounded sort of a region of complex plane. So to satisfy basically overshoot condition, you have to be within this region, okay? And finally, the last condition that we were given is the rise time. So rise time should be smaller than 0.6 seconds. So if you remember now the formula for rise time, roughly speaking, rise time is 1.8 over omega n, where I remind you omega n is the natural frequency. That's the distance of the pole to the origin, right? That's the omega n, right? So, and the condition that we have here is that the poles should be outside this circle here. In other words, the poles should be in this shaded region. So when you how did we do that? Well, we are given rise time specification. We upper bound the 1.8 omega n, and we just calculate omega n should be greater than 3, right? From that formula that is given in the lectures. Now, in order to satisfy all three conditions, all of these three guys, right, we would need to basically place the poles in the intersection of all these three regions, right? So what you get in the end, well, the vertical line was here, and then when you intersect the overshoot region with rise time region, you get something like this. So actually, the settling time condition is sort of more relaxed. So we have to strengthen the condition in order to just satisfy overshoot and rise time conditions. So intersection of all these three regions is given by this shaded region here, right? By the way, the vertical line coming from settling time is here, right? But since we need to work with an intersection of all three regions, well, this is what we get. So we need to place all poles in this region in order to satisfy all the specifications. So if you remember, we did root locus today. In general, you would be first asked to translate specifications into locations of closed-loop poles, and then play with controller parameters to see whether you can place the poles in the desired region. That's the design, right? In this specific example, you know, we were just asked to first, well, specify the region, and then it says here, indicate specific location that will have the smallest rise time, an overshoot of smaller than 70%, and also meet the settling time specification exactly. So now we are looking at the B. So if the settling time is 9.2 seconds, then we have to have exactly that the real part of the poles is 0.5, exactly, right? So therefore, poles should be exactly on this vertical line that corresponds to that particular settling time. And then to make the rise time small, we would need omega n as large as this, and then the overshoot condition would be satisfied if the poles are located in any of the, you know, shaded region, right? So basically, where do we want you know, poles in this case? Well, if it's exactly the settling time condition, then the poles should be exactly located in these two locations, right? Because that's then corresponding to settling time being exactly 9.2. So if the real part of the poles is exactly on this vertical line, right? So that's that. And then the second one was saying also meet settling time specifications exactly. So this is the overshoot and settling time. And then it says specific location that will have the smallest rise time, right? So let's look at that. So the rise time, you know, condition would, so rise time is related to omega n in this way, right? So basically, if we want to say rise time is, let's say, smaller than 2, then again from this formula we can calculate what the natural frequency should be. So that means that we should be somewhere, you know, on this circle here, right? Because that corresponds exactly to this. If we are outside this circle, then the inequality can be used. And then, you know, because we were told that we are allowed to have overshoot just smaller than 17%, then we can work with inside that shaded region, right? So then, in this case, if I say, for instance, overshoot is smaller than 10%, that would correspond from that diagram in lectures to the damping of 0.6, and this is roughly the angle of 36.8. If you take arc sine of 0.6, you get angle of 36.8. So the region where these dominant poles you know, should be, you know, to satisfy overshoot and rise time, you know, would be this shaded region, right? So now, I mean, what's given later on, this is not asked in the question, but it shows you what happens. So this shows you basically rise time. If you look at the step response, what is shown here is what rise time is? Well, it's the time needed for response to go from 10% of the final value to 90%. So this time here is exactly the rise time, right? And settling time would be the time needed for response to get to within 1% or 5%, depends on the definition, of the final value and stay there forever afterwards. So this would be the settling time of 9.2. So these are basically responses that you get from various selections of locations of poles, right? So note that if you have more damping, you know, your response would be less oscillatory, right? If you have less damping, this corresponds to less damping, this corresponds to more damping, all right? Here, rise time is larger than here, so you can say that in terms of rise time, this response is faster than this response, because rise time here is smaller than this rise time. And then here's this settling time here is smaller than that settling time. So in terms of speed of convergence to y infinity, this guy converges closer to y infinity than this guy. And both of these responses correspond to specific selection of poles that we did earlier. So in some sense, you can map where the poles are to what the step response looks like, and then features of step response are captured by the things that we discussed earlier. You would be, in general, given, you know, different types of specifications, and you would typically use these three formulas to come up with different, you know, regions in the complex plane where you have to move your poles. And then you would learn different techniques like root locus you learned. You will learn how to tune PID controllers, and you would learn pole placement, and you would be able, with these techniques, to move the poles of the closed loop in the desired region. So that pretty much many examples would be like this. You first translate specifications, you know, and then you design controller that satisfies these specifications. In this case, you know, we were not given a controller. We were simply given a transfer function, and we were asking, well, select the poles of the transfer function so that we satisfy certain specs. But in general, you would have this maybe to be a planned transfer function, and you have to connect it with a controller, and then play with the controller gains to achieve what you are asked to do. Are there any questions regarding this? Yep.
In question 2, there's a condition that there's no finite zeros in the question 2.
So
I think that the zero will
here
affect the omega n, right?
Zero. Well, zero would be changing the transfer function. There may not be omega n at all. I mean, there would be something there in the numerator that's different from omega n squared. The formulas that we gave in the lectures apply exactly to just that class of transfer functions. If you have a zero, if you remember when I talked about fundamental limits, we were looking at a transfer function, an example where there was a zero, either stable or unstable, and that was plotting step responses for different values of the zero. You could see that those step responses were genuinely different from this step response that we are getting for this class of transfer functions, because sometimes we were getting undershoot. For unstable zeros, we're getting undershoot. So these formulas that we are using here are rule of thumb for systems that may have zeros and things like that, right? Just rule of thumb. We will still use them, but they won't get you exact things. But you know, if you use these rules of dominant poles, it would get you close to it. Mm-hmm. So the second question is very much the same as what we had before. So I would say do this as an exercise. Actually, this is included in solutions, right? So since it's a start question, it is included in solutions. Now this is, by the way, taken from control systems final exams. So sometimes in final exams you may have short questions, or this can be part of a larger question, and this was taken from some of the exams. Let's look at this one. So question 9, final exam 2016. Suppose you design 2 controllers for a given plant and they both yield a stable closed loop system. All right? The first controller gives you rise time 0.5 seconds and settling time 10 seconds. The second controller gives you rise time 1 second and settling time 4 seconds. Which controller gives you faster response for the closed loop system? All right, so this is, I want to check how your sort of understanding is of these topics. What do you think? Which response is faster?
Smaller TR.
Sorry?
Smaller rise time.
So you are going with smaller rise time. You're saying that's a faster system. Okay? What do others think?
Shouldn't be the smaller settling time, since the closed loop system is to want to achieve the equilibrium faster.
All right. So we have rise time and we have settling time, right? So does this cover all possibilities? Sorry? Well, actually, the correct answer is we can't talk about it in that one is faster than the other. One is faster in one sense, but slower in another sense, and another one is faster so one is faster in a sense that it reacts quicker. Small rise time means that the system is more reactive. But then since settling time is longer, it means it takes long time to settle, right? So when you think about convergence to where you want to go, that's slower, right? But the question is, how do you want to measure? The correct answer is, well, depending on how you want to measure what is fast, right? Then either one can be chosen, or you can say, well, neither one is actually faster than the other. One is faster in one sense, but slower in another sense. So that's the correct answer, because the point here is that each of these features captures a different property of the step response. That's the point. So overshoot, rise time, settling time are all genuinely different things. So you can't just say that one is more important than the other, right? And that's the correct answer, right? I like to ask questions like this, by the way, just so start getting used to it. So let's see. All right, so this is an interesting one. Again, this is taken from one of my exams. By the way, this subject is run in 2 semesters, but all of these questions are taken from my exams. So I will be writing the exam for this semester, so they are more relevant for what you might encounter in the exam situation. So let's just think about this question. So I want to see how you think, right? I want to see whether you can figure out this one. So what you are asked here is, suppose that you have found that the characteristic polynomial or closed loop takes this form, right? So where Kp positive is a controller parameter that you can tune. So think about this polynomial as a denominator of the overall transfer function. So there's a controller, depends on a parameter Kp, there's a plant, maybe in a feedback loop, you found the transfer function for the full system, and in the denominator of transfer function you get this polynomial. So now obviously, depending on how you choose Kp, you will have different zeros of this polynomial, which are actually poles of your transfer functions. And you are asked here, explain how you can use Routh-Hurwitz criterion to check if the settling time, 5% of the final value, is smaller than 2 seconds. You do not need to complete all calculations, just explain the steps that you would use. All right, that was one of the short questions. So this tests your knowledge. It doesn't test your mathematical prowess. You know, it just says, well, do you understand what you need to do? And describe what you need to do. So does anyone have an idea how to use Raud-Hurwitz to check this? So I remind you that Raud-Hurwitz criterion is used to check whether a polynomial has all its roots or zeros with strictly negative real parts, right? You can also check how many are with positive real parts, but I didn't present that result. If you just want to check stability, you can check whether all, poles have strictly negative real part. So, but here I'm asking you something else. I'm saying I want you to achieve certain settling time, but I want you to use Raud-Hurwitz to verify this. I actually showed you this in lectures. I explained this in lectures. This is a couple of slides in the lectures. When I talked about Raud-Hurwitz criterion. So the first step would be, obviously, we want to see what's the region in the complex plane where, solution, where poles should be, right? So we are given settling time. So what does the region look like? It's to the left of a vertical line. And we calculate where this sigma that intersects, this line intersects the real axis in complex plane is from settling time condition. Right? So the formula is exactly the same as the formula that we used here, right? So this is the formula. I gave you now in the exam, I gave you, what, 2 seconds, right? So in the exam, you are asked to do 2 seconds, right? And over there, it was 9.2 seconds. So you just substitute this by 2. So then sigma should be larger than 4.6 divided by 2, 2.3. So then you get a vertical line, and all your poles have to be to the left of that vertical line. So what you can do then, you can play that trick I explained in the lectures. You can first introduce like a change of coordinates so that you shift the real line, sorry, imaginary axis to point minus 2.3. How do you do that? You introduce a new complex variable w, which is s plus whatever, 2.3. And then you rewrite this characteristic polynomial in w, and if you apply to that new characteristic equation in w Raud-Hurwitz criterion, then you are to the left of this vertical line 2.3. So this takes 3 lines to describe what you need to do, right? And I was not asking you write down Raud-Hurwitz, do blah, blah, blah. Just use Raud-Hurwitz to enforce this or check whether you can find this KP that places poles to the satisfying this condition on settling time. So it's you have to just, you see, some questions I ask are sort of trying to connect, you are asked to connect things. And that requires understanding. Right, so you need to understand. And typically these short questions, if I give them to you, sometimes I give short questions, sometimes I don't. But if you are given these short questions, typically either you can do it in 2 minutes or you won't be able to do it. Because it requires understanding. It doesn't require solving things for 5 days, right? Writing 5 pages, right? Okay. Are there any questions? Sorry?
Why do we use the same formula?
You're right. Maybe so. I can't remember. This one is, I think, given for 1%, right? So in Ogata, you will have different formulas for different percentage values, right? So that's true. But in any case, even if you told me, I will use a formula for 5%, you don't have to tell me what the formula is. You will get full marks. Just as long as you explain the steps. So I'm not asking any calculations, just steps which show your understanding of what you need to do. So a specific formula is not needed.
And I didn't understand how we shift the imaginary axis.
So, all right, let's just do it. So we did that in lectures, but let's do that now. So I will just switch to document camera. So suppose that you have polynomial which is s plus k, and you are saying you want to just consider s plus k equal to 0, right? That's one example, right? So if I say what's the solution of this guy, right? Well, the solution of this guy, maybe I should denote it as lambda, right? Lambda 1 is minus k, right? So, but then that says that in these coordinates, so this is a real part of S, and this is the imaginary part, j times imaginary part of S, right? In these coordinates, this is the location of this point, yeah? So, but what I can say is, I can say, well, suppose that I introduce new variable, complex variable w, which is basically given by, let's suppose it's given by s plus 1. I decide to define this new variable w, so this small triangle means definition. I introduce the definition of this new variable w. This is the same as actually changing the coordinates of your system. Why? Because if I rewrite everything, so I now have my polynomial, which is trivial, s plus k, right? But I want to say, well, what is s from here? Well, s is w minus 1 by definition. This is just what I defined. I decided to define it this way. And then what I can say, well, since s is w minus 1, I can replace s into this equation and rewrite everything in terms of w, right? So I can say this is the same. The original equation is the same as w minus 1 plus k equals 0. Do you follow that? So now I say, well, my w is what? 1 plus, sorry, minus k, right? But then, look, what does this mean? Well, w now is, I'm adding 1. So if k was in absolute value larger than 1, I would say, well, w now is somewhere here, but the point is I shifted the real axis by 1. So when real part of S is basically minus 1, then the real part of w is 0. Does that make sense? So what I can do is I can say, suppose that, why is this significant? Suppose that I want to put all the poles to the left of some line which intersects a real axis is minus sigma, right? Well, what I can do is I can substitute, I can say, well, let me introduce S, which is basically related to some w plus something. So the question is, what do I put here so that I shift this imaginary axis in w coordinates? This will become the imaginary axis in w coordinates, right? So how can I do that? What do I have to put here? Anyone? What do you want to achieve? You want to achieve that when basically a real part of S is equal to minus sigma, right? Then real part of W would be 0. That's what you want. Sorry. So this is what you want. You're changing, you're shifting, you are translating imaginary axis by a certain amount. And the question is, you need to add, so you need to introduce new variable W so that S is equal to W plus something. You need to figure out this something from these two conditions. So there you go. Yeah? So, and then what you do is, if you have here, what, minus sigma, right? So when real part of W is 0, then real part of S is minus sigma. When you rewrite everything in W coordinates, then checking that real part of W is negative is the same as saying that real part of S is smaller than minus sigma. And then you just introduce this change of coordinates, you rewrite your characteristic equation in W, and then apply Raud-Hurwitz to W, no longer to S. I see more people nodding, so I hope that this is clear. Is it clear? I mean, now? I don't see nodding from where the question came from. Is it clearer?
How can I know the settling time is smaller than 2 seconds from this?
Because you can relate. So first thing is you need to tell me what is the vertical line that relates to that settling time in the complex plane, right? There is some formula. And that gives you the vertical line. So there would be a formula, like the one I presented over there in the previous example, 1 point something divided by, or 4.6 divided by, you know, TS.
I can get the sigma from the settling time.
Yes.
And shift the imaginary.
By that amount. Yes. Excellent. I heard, ah.
Yeah.
Excellent. All right.
For the settling time, if it doesn't state, for example, 0.1 to 0.9, can we assume it's 0.1 to 0.9 if it doesn't state the definition?
If I don't give you specific requirement which settling time to use, you choose your own and you just tell me I'm using, since it's not given, I'm using this. I won't, you know, look, when I'm marking, I don't ask for, you know, everything to be, like, I'm not testing your calculations, your ability to add numbers or multiply numbers. Obviously, you lose a little bit of mark if you do not add things up or calculate things correctly. But I test for understanding. So if the procedure is clear, right, you would get pretty much like close to full marks. Just if the procedure is correct. Obviously, if you are making big mistakes, what are the big mistakes? You know, it's like, you know, writing down transfer function for the feedback connection with the wrong sign. That's a big, so some students say, oh, this is a small error because it's just plus minus, but that's a big conceptual error. All right, let's see whether we can do anything else. It seems that this is it. All right. All right. Let me just use this opportunity. I ask you one question regarding the root locus today, because next time we will soon start looking at root locus. So as an introduction to the next tutorial, I just remind you that in today's class, we considered an example where root locus looked something like this. So there was a and then I think there was one guy here. So the root locus had, you know, a pole at the origin. So the open loop transfer function, pole at the origin, pole at some other point here, and then there was another pole here. We had one asymptote, vertical asymptote, right? And then maybe there was a zero here, I can't remember. Was there a zero here? Yeah, so zero here. Now, know that this part was far away, so we could really talk about dominant poles. These two branches would correspond to dominant poles. Now, I wanted you to think about how changing the gain, so I just remind you, as you change gain in your controller, right, then the roots of your characteristic polynomial or denominator in your transfer function move in this way. So two roots, two poles would move towards each other. They would meet here. They would separate, and then they would tend to these asymptotes as gain goes to infinity. And this guy would stay always on the real line, but this guy is further away from the imaginary axis, so we can sort of forget about it because we can just concentrate on the dominant poles. So can you now tell me how does increasing gain affect the system's performance in terms of overshoot, rise time, and settling time? So we did all these things on the previous examples, so I'm applying it now to the root locus example we had today. Let's first talk about the overshoot. So what would happen to the overshoot? As I change gain from 0 to infinity, as I change gain from 0 to infinity, these two dominant poles would keep moving like this. They would meet, they would split, and then they would go towards asymptotes. What happens to overshoot? Sorry? It will be bigger. As long, very good, thank you. So as long as we are on the real axis, we have an overdamped response because, you know, there is no overshoot, right? So once we meet, like once we reach this triangle and we split, then we will start having overshoot. How much overshoot? Well, roughly, because we have this extra pole which would sort of make things slightly imprecise, but roughly, you know, if we are at this point, obviously all poles would always be complex conjugates. So if we chose the gain so that poles are here, you have to draw a line through these poles, and that would give you the angle that you have with respect to imaginary axis, and you can calculate from there damping. As these poles travel, as you increase the gain, the poles travel on this branch, and then they would do this, right? So the damping factor will become smaller and smaller as we increase gain. That results in larger and larger overshoot. The smaller the damping factor, the larger the overshoot, right? How about settling time?
Come to a point, then to nothing.
Very good. Look, as we increase, what we need to look at is, as we increase gain, are all both the dominant poles to the left of a vertical line, right, that intersects the negative real axis at this minus sigma. So as you increase gain, this pole is moving, so this branch, pole corresponding to that branch, is moving towards the triangle. This guy is always to the left of this pole, so we can say that settling time is really determined by this guy, right? And then when they meet at the triangle, then settling time would correspond to this line here. But as we keep increasing the gain, then settling time starts decreasing because our poles are getting closer and closer to the asymptote. We sort of start, you know, getting again a larger settling time because we have a slower response. We have faster settling time at the triangle where these two branches meet. When they separate, then they will start moving towards the asymptote, but asymptote is to the left. So we will be, again, getting longer settling time. We get a slower response. In that sense, How about rise time? So for rise time, what do we need to look at is circles, right? So we are looking at, so basically, if your poles are here, you need to look at this semicircle, right, that passes through these poles, and the radius, that's your omega n. Omega n is related to rise time. It's inversely proportional with some constant of proportionality, right? So the larger the omega n, the smaller the rise time. So what does this mean? As we increase gain, we get smaller and smaller rise time. So let's put these things together. For a while, you get no overshoot at all. Increasing gain starts increasing the overshoot. Rise time, it's sort of improving as long as you are increasing the gain. It's shorter and shorter rise time. So in terms of rise time, we are good. But in terms of settling time, we will be getting faster and faster convergence up to a point. And then if we keep increasing the gain, we will get slightly slower convergence as these two branches converge to the asymptote. So can you now appreciate what we are doing here? We are doing design, but we have specifications that we can translate into locations of poles. So everything fits together. And I think this tutorial was a very nice sort of introduction to actually what I asked you to think about after the lecture today, right? So what you would gain from root locus is a lot of intuition. If you know how to use this tool, it's a simple tool, but you will gain a lot of intuition. So learn it well. Learn it well. Lots of things will depend on that. All right. Are there any questions regarding this? I think this was very sort of related to what we were doing today in tutorial anyway. All right, well, thank you very much. I can't believe I managed to deliver 3 lectures today, and I'm still recovering from my cold. So thanks for being patient with me. I'll see you next week. Hey. So let me just take off the mic. So note that as we are as we are increasing the gain, this branch, pole corresponding to that branch, will be moving in this direction. So as that pole moves, that's the closest pole to the imaginary axis. That will determine the amount of settling time. And that would keep sort of, because this distance here from the pole closest to the imaginary axis is inversely proportional to settling time. So the larger the distance, the smaller the settling time. So the settling time will keep reducing up until we hit this triangle. But then, since the branches are separating and then they are converging to the asymptotes, then the settling time would actually start reducing. So the distance is reducing from the imaginary axis, and then the settling time is increasing. So in terms of settling time, we are doing better and better and better up until this point. After that gain, we'll be sort of making settling time larger and larger again. And there is definitely a limit to that, and the asymptote gives us the limit to what is the longest settling time with any gain.
So as a reference of this taking that the nearest pole to this asymptote, can
we look at dominant poles. Always the dominant poles are the closest to the imaginary axis. We always need to look at that.